Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic.
Welcome to the show, folks. Today we're diving into deep learning for intrusion detection with a focus on tree-based models, ensemble methods, and clustering techniques.
Oh, absolutely. I've been waiting for this discussion. What's the first element on the agenda?
Well, to kick things off, we're starting with decision trees. They use a sequence of questions to classify data, like determining if an animal has horns or counting its legs. It's like a systematic narrowing down of possibilities.
Yeah, it makes you wonder, right? How such simple questions form the backbone of a complex classification system.
Exactly. And the technique of choosing splits in decision trees is fascinating, using information gain, which basically measures the decrease in impurity from parent to children nodes.
Right.
That calculation is what makes the tree as efficient as possible, minimizing unnecessary splits.
Yep. And speaking of efficiency, the method of optimizing information gain resonates with the concept of, cutting through clutter to get to the heart of the matter.
Absolutely. And there's also an interesting twist when it comes to regression trees. Instead of voting on a class, each leaf node produces a mean value from the target values. So it's tailored to predictions like numeric estimates rather than classifications.
That makes sense. But don't you think that with regression trees, there's a risk of oversimplification if we use a mean where the data is really skewed?
That's a valid point. It really depends on the variability within the leaf. Some might argue that majority voting in classification is cleaner, but for regression, the mean can average out the noise. Still, you need to be cautious about outliers, though.
Exactly. Outliers always have a way of causing a bit of havoc in these models, don't they?
Moving on from decision trees, let's look into ensemble models. Ensemble models, like random forest, combine multiple trees to boost prediction accuracy by reducing overfitting. They essentially average out the predictions from many decision trees.
That's the beauty here, isn't it? Instead of relying on one potentially erratic model, you pool results and get something much stronger.
Exactly. It's like having a panel of experts, each giving their opinion, and then you take a consensus. And then there's AdaBoost and gradient boosting, which build models sequentially. Each new model learns from the mistakes of the previous one.
Right. And I love that analogy. It is like iterative learning, fixing the errors as you move along, each iteration honing in on the misclassified data.
Exactly. And with AdaBoost specifically, you start off with equal weights and gradually increase weights on samples that are misclassified. Over 100+ iterations, you get a system finely tuned to the errors.
But what do you think about the computational load of these ensemble methods? They must be a bit heavy compared to single decision trees.
That's a fantastic point. Ensemble models, despite their robustness, do demand more computational resources and time for both training and prediction.
Right.
It's a trade-off between interpretability and performance, since ensembles can be less transparent compared to a single tree.
I can see that. Sometimes you really need the extra computation, but other times simplicity wins.
Now, shifting gears a bit, let's talk about clustering. This area is all about grouping data points based on similarity without the luxury of pre-labeled groups. It's crucial for exploratory data analysis and even in customer segmentation scenarios.
Right. And it's interesting because it poses a different challenge. How do we measure similarity in the first place?
Exactly. Determining the basis for similarity and selecting the right measure is a key decision. It often involves calculating distance or other similarity metrics that work best with the data structure. It's all about context and purpose.
Yep, and that naturally leads us to k-means clustering, doesn't it?
Yes, k-means is a prime example. It works by assigning points to clusters based on their distance from a center, then recomputing those centers until the clusters eventually stabilize. It's iterative, reminding me of the repeated refining we see in boosting algorithms.
Absolutely. There's a recurring theme here of iteratively improving, whether it's decision trees splitting more effectively or clustering centers moving to reduce variance.
Yep, exactly. And k-means, while fast and simple, does come with its own challenges. For one, you have to specify the number of clusters beforehand, and it tends to assume linear cluster boundaries, which can be a real limitation.
True. And if the actual data distribution is complex, those assumptions might not hold, leading to suboptimal clustering outcomes.
Right? That's why sometimes alternative clustering methods might be needed if the dataset has intricate structures. But overall, k-means still shines for quick initial exploratory analysis.
And it's fascinating to see how these methods, decision trees, with all their splits and ensembles, compare and contrast with clustering techniques.
Exactly. They each have their unique strengths. Decision trees are great for interpretability and handling nonlinear relationships, whereas ensemble methods build on that foundation to drive accuracy even further. And clustering, on the other hand, is unsupervised, giving us insights without the confines of predetermined labels.
So it's really about picking the right tool for the right job, isn't it?
Precisely. Now, one thing I always find intriguing is how these methods relate to each other in practice. For instance, ensemble methods like random forest leverage the simplicity of decision trees, but mitigate their overfitting issues. And yet, each tree in a forest might individually be weak, but together they form a robust predictor.
True. But I sometimes wonder if the loss in interpretability due to ensemble averaging is worth the performance gain.
Your skepticism is valid. There is indeed a trade-off here: better accuracy versus a more opaque model. In applications where explanation is crucial, a single decision tree might be favored despite its limitations.
Right?
It's all about weighing priorities.
Well said. And speaking of trade-offs, do you think that the computational overhead of boosting algorithms like AdaBoost and gradient boosting discourages their use in real-time intrusion detection systems?
That's an interesting angle. While they are computationally intensive, the iterative accuracy improvements they provide can be invaluable, especially when detecting subtle intrusions. In contexts where real-time response is less critical than accuracy, the trade-off could be justified.
But if you needed lightning-fast decisions, maybe a simpler model would be preferred.
Exactly. It's like choosing between a souped-up sports car and a reliable commuter. Each has its place depending on the journey. Intrusion detection could go either way depending on the specific requirements.
On a final note, let's quickly touch on the benefits and challenges of decision trees. They train quickly, require no feature scaling, and handle nonlinear relationships well, correct?
Yes, that's absolutely right. Their interpretability is a major plus. But setting tree depth correctly is vital, because if it's too deep, you risk overfitting, while being too shallow could lead to underfitting.
And that brings the conversation full circle, showcasing that every model has its sweet spot based on its design and intended purpose.
Exactly. It's like each method has its own unique DNA, designed for specific tasks in the realm of machine learning for intrusion detection.
Yeah.
It's all about matching the algorithm to the problem at hand.
Incredible insights today. I love how we've linked these concepts with everyday analogies. It really helps demystify the technical details.
I'm glad you're enjoying it. The interplay between trees, ensembles, and clustering shows that even complex systems have an underlying simplicity if you look at them the right way. It's been a robust and engaging discussion today.
Indeed. Thanks for the deep dive and for breaking down these sophisticated concepts into digestible ideas.
Anytime. Until next time, keep exploring the fascinating world of machine learning and intrusion detection. There's always something new to learn.